Hi class, we're now on 17.8, acid-base properties of ions and salts. So the salt, if you remember that neutralization reactions, and then I did briefly discuss the net ionic equation when we look at a neutralization reaction, is that it produces the H plus and the OH produces water. That's the net ionic equation. The salts that are attached to the anion and cation, those are we would just refer to them as the salts that are left over that don't participate in that reaction. So we're going to now look at those salts. Salts are ionic compounds. They are soluble salts that form ions in solution. The anions tend to form basic or neutral solutions. The cations tend to form neutral or acidic solutions. And salts that form the neutral solutions, so if we look here at the anions and the cations that form neutral solutions, those are the counter ions, so those are attached to the strong acids and strong bases. So for instance, if you think of sodium hydroxide is a strong base. The salt that we're looking at is sodium, and that forms a neutral solution in its presence. So salts that don't form neutral solutions contain one of the following, and we're going to go through these. A cation, that is the conjugate acid of a weak base, or a small highly charged metal. So we can look at, for instance, we have ammonium and ammonia. That could for the first one, and then a highly charged metal would be something like aluminum. An anion that is the conjugate base of a weak acid. So HF is a weak acid, and we have the fluoride ion. Cation of a strong base and anion of a strong acid do not ionize water, hence they don't affect the solution pH. So if we look at the sodium here and the chloride here, they are neutral because they are attached to a strong acid or a strong base. The cation of a weak base and anion of a weak acid will ionize water and affect the pH of a solution. So for instance, we have sodium bicarbonate. Sodium we've already discussed, but the bicarbonate is this is hydrogen carbonate, is a conjugate base of a weak acid. So with the proton left, this is the conjugate base. So this will affect the pH of a solution. So every anion can be thought of as a conjugate base of an acid. So if we understand this, it says every anion can be thought of as a conjugate base of an acid. Okay, so if we look at this reaction here, we have water, and if we follow where the proton goes, remember we need a lone pair on the base. So if we go this way, we see that the proton is transferred to the base, and then it ends up creating an anion from the acid because of the proton being left. So the stronger the acid, the weaker the conjugate base, which is the anion from the salt. An anion that is the conjugate base of a strong acid is pH neutral. So again, if we're looking at the counter ion of a strong acid, it's not going to affect the solution. So it's going to be its pH is neutral. So an easy one to look at is HCl. The chloride ion is not going to affect the solution, so it will stay pH neutral in its presence. An anion that is the conjugate base of a weak acid is basic. So in this case, we have a weak acid that is HF, but the fluoride ion will affect this solution because of the fact that it is part of a conjugate acid and base. So this is going to be a basic solution. So a weak acid, once it in its anion form, will form a weak base. Oh, I went too far. So here we go. We have a chart here that shows you what is considered strong, what is considered weak, and then we have negligible. So this would be good to also understand this should be listed in acid strength, so you can see which acids are stronger than others. And the same with base. The base strength is down, so here is strong, and here is weak. So it starts here as neutral, and then it goes to weak, and then to strong. So this would help you if you have some questions about what you're looking at. Okay, so which anion acts as a weak base? So remember, a weak base, if we look here, an anion that is the conjugate base of a weak acid is basic. So if we're looking at the anion, we want to look at something that is part of a weak acid. So the weak acid, the anion is going to be a weak base. So in this case, it's going to be not HCl or bromide, it's going to be the fluorine, because fluorine is a part of a weak acid, so the anion is going to create a weak base. Which and there's the answer right there. Okay, so cations. The stronger the base, the weaker the conjugate acid. So a cation that is the counter ion of a strong base is pH neutral. That's the easiest ones to understand. If you want to know what strong acids and strong bases are, you know that the cation or anion is going to be neutral. A cation that is the conjugate acid of a weak base is weakly acidic. So in this case, we can look at this here. So it says a cation that is the conjugate acid of a weak base. So here is a conjugate acid of a weak base. This is going to create an acidic solution. So it's going to be weakly acidic. And so when we think of the terms, so if you realize the strong acids and strong bases, the cation and anions don't affect their pH neutral. But when we start looking at weak acids and weak bases, then those cations or anions do affect the solution. So a cation that is a small highly charged metal ion forms weakly acidic solutions as well. Okay, so now let's look at that. Metal cations as weak acids. Cations of small highly charged metals are weakly acidic. Alkali metal cations and alkali earth metal cations are pH neutral. So we're talking about group 1 and group 2. They are neutral. Cations are hydrated though. These can be weak acids. So an example would be iron 3 or aluminum 3. They are hydrated is a Bronsted lauric acid proton donor, which I'm going to explain what this means. So if we look at aluminum here, the aluminum chloride is dissolved in water. The chloride does nothing, it's pH neutral because we already know that from HCl. The aluminum ion is hydrated by 6 water molecules. So water attaches to this molecule and creates a structure. When it does that, now it has the capability of losing a proton. So the aluminum ion hydrolyzes one of the water molecules to release a proton. So that's what you see here is that it has 6 water molecules attached, but then it ends up losing a proton. So it has 5 water molecules attached and a hydroxide ion. So by donating this proton, it now creates an acidic solution. So added together, that's what you're seeing with this overall reaction, is that by itself, it can take on those waters. Once it takes on the waters, it can release one of the protons, thereby creating an acidic solution because of it. It still holds on to the hydroxide, but it can release that one proton. Certain metal cations act as acids. These metals have high charge density, so high positive charge and small ionic diameter. Here is an example of some of them: aluminum, iron 3, chromium 3, copper 2, zinc 2, and cadmium 2. These are all capable of hydrolyzing water, which means that they can create acidic solutions. So these ions interact with water molecules, they form the hydrated ions, and once they can do that, they can release the protons into the solution. So here is counter ions. So if we have a strong acid, here are the anions of the strong acid, and here is a strong bases, and here are the cations of strong bases. So any combination of these create a neutral solution. So these are really good to understand that if you have any of these, they're not going to affect the pH of anything. So if the anion is a conjugate base of a weak acid, such as acetic ion, and the cation is from the table, then the salt forms a basic solution. So let me explain what this means, is that this is a weak acid. So if this is a weak acid, its conjugate base is also now a weak base. It's attached to any of the salts on this table. Those salts kind of cancel themselves out because they're neutral. So if they're a part of this, they don't matter. So we're only looking at what is the anion. And the anion, so if you have a weak base, a weak acid, the conjugate base is now basic. So this is now creating a basic solution. Anions are strong acids and cations are strong bases. They have no acid-base character. So even if this was a sodium acetate, the sodium doesn't play into it because of the fact that we've already covered why it's neutral. Cations that are conjugate acids of weak bases are acidic, and anions of conjugate bases are weak acids are basic. So the easiest way to try to remember this is that if you're dealing with the weak base, the counter of that is also going to be whatever this. So if this is a weak base, then the counter ion of it is going to be acidic. And if you're dealing with a weak acid, then the conjugate base is going to be basic. So it's the opposite of what you're dealing with. The ion with the stronger acid or base properties will determine if the solution is acidic or basic. So we're talking about weak acid and weak bases. So if you have something two in there, the one that's stronger is going to determine the solution. It's basically, in a sense, going to cancel out what the other one is. So for example, ammonium phosphate has a conjugate acid as the cation and a conjugate base. So sorry, I was thinking of we cover this later. So if we look at this, this plays a part in affecting the solution, and this plays a part in affecting the solution. So the one that's stronger is the one that's going to determine the pH of the solution. So the phosphate ion has a stronger base. It's 2.1 times 10 to the negative 2. And ammonium ion is 5.6 times 10 to the negative 10. So that's very weak compared to the Kb. So this is going to result in a basic solution of ammonium phosphate because of the phosphate ion. So which ionic compound forms an acidic solution when dissolved in water? So if we look at this, we know that this and this is not going to affect, this is not going to affect, and this will make it acidic, slightly acidic. Sorry, this is slightly basic. So this isn't going to apply, this isn't going to apply, but this one is. Why would this one apply? Because Br is part of a strong acid, so this anion doesn't participate. However, this ammonium is a part of a conjugate acid base pair with ammonia, so this is going to be slightly acidic. Is going to be acidic because ammonia is a weak base and this is its conjugate acid. So this is going to create an acidic solution in water. Okay, so relationship between Ka of an acid and Kb of its conjugate base. So this is simply showing you where the Kw comes in when we're dealing with an acid and a base. If we multiply these together, so here we have general equations for a Ka and a Kb. And if we multiply, bring everything down here, and then we set it up here, it's basically multiplying it out. Everything cancels out except for the hydronium ion and the hydroxide ion concentration, which still gives us Kw. All right, and this is exactly the same slide. It's just a little cleaner to see what's going on. We have our Ka, we have our Kb. We put these together. We can cancel out what is matching here, canceling out those, in a sense, units, and it leaves us with the same thing. Okay, so now we're going to get into calculating. The strength of an acid or a base is inversely proportional. It has to be, because if it's equal to Kw, which is a constant, one has to go up, the other one has to go down in order to stay with that constant value. So the stronger the weak acid, the weaker its conjugate base, and vice versa. So the strength of a weak acid and that of its conjugate base are related to the equilibrium equation. So we expect if we're dealing with a Ka that's strong, then the Kb is going to be weak, and vice versa. The pH of a salt can be calculated if you know its concentration and the Ka and Kb for the acidic or basic ions that make up the salt. So this is where we're leading to here. So let's take a look at pH of salt solutions. We have a cation. It's a conjugate acid of a weak base. We have an anion. It's going to be acidic. Anion depends on relative strength. Cation, small, highly charged metal ion, is going to be acidic. The anion depends on relative strengths. Cation, counter ion of a strong base, is neutral, and the anion is basic. So basically, these we know, if you have this, it's acidic. If you have this, it's going to be acidic. And if you have this, it's going to be acidic, because the conjugate base of a strong acid is not going to affect it the way that the cation will. And then when we look at the anion here, a conjugate base of a weak acid, this is where we'd have to look at the Kb's to the Kas to determine what's going to happen here on this one. So is ammonium nitrate acidic, basic, or neutral in an aqueous solution? Okay, so cations that are conjugate acids of weak bases are acidic. So remember, think of it this way. If you have a weak base, then the opposite of what it is going to match the opposite. So if you have a weak base, then the counter partner, if you want to say, and not just say conjugate acid, but its partner is going to be, the opposite partner is going to be whatever it's not. So if this is a weak base, is basic, then the opposite is going to be acidic. So in this case, we have a weak base. So what I'm trying to say is the conjugate acid, without saying conjugate acid, because that might seem more confusing, but whatever it's partnered with, when the transfer of a proton is going to be the opposite. So if this is base, this must be acidic. Anions of strong acids, again, have no acid-base character. The nitrate is the anion of a nitric acid, and thus has no acid-base character. So this one is also one that we wouldn't pay attention to. Will dissolving each of the following salts in water raise the pH, lower the pH, or have no effect? Okay, so let's just look at these and go through them. So here we have no effect. Barium is a large cation and not a conjugate acid. So this is not going to play into anything. And then we have ClO4 minus, and it is the counter ion of a strong acid. So neither of these play into having any effect on the pH. It's going to be neutral. Now we have iron 3 nitrate. Well, we just discussed nitrate, and nitrate has no effect because it comes from a strong acid. So what we need to look at is the iron. Iron is a highly charged metal, so this will affect the solution and create, it will decrease the pH because it'll make it acidic. And here we have copper 2 sulfate with waters. Here is a copper ion that has hydrated itself with 5 waters. This means that this can donate a proton from one of the 5 waters. So this is going to also decrease the pH, just like the aluminum example I did in a few slides prior. Okay, so the Ka of formic acid is 1.7 times 10 to the negative 4. Calculate Kb of the formate ion. So this is where we're going to use the Kw, because we remember these are related to the Kw by multiplying them together. So as long as we keep the constant, we can solve for the other one. So we set it up with the constant and solve for Kb, and we get 5.9 times 10 to the negative 11. And you can see as one is higher, one's got to be weaker. Determine the pH of 1.0 molar solution of sodium acetate. Ka is 1.8 times 10 to the negative 5 for acetic acid. So if in order to discover the pH, we need the hydronium concentration. So here, let's take a look at what we have here. So we're going to start Kb for the acetate ion and then set up an ICE table. Okay, so we need to set up an ICE table for this. Why? Because we're dealing with a weak acid, and a weak acid or weak base. And remember, when we do, we are affected by hydronium content and the hydroxide content. So we need to make sure that we are actually dealing with whatever is the weak acid or the weak base. So we set this up, and the sodium doesn't come into play with this because of the fact that it doesn't affect the solution at all. So we want the Kb. So remember, we want to know what the hydroxide concentration would be for in this case. So we bring it with the acetate ion plus in a combination of water, and we have the equilibrium arrows with acetic acid and the hydroxide ion concentration. So we set this up, and hopefully by now this seems sort of familiar of how to do this. Now we place so we set it up, x squared. We're going to do the assumption that this x is small, that we can ignore it, which makes it easier to do this equation. And we're going to set this up and solve for x squared. So we do the square root, and that gives us 2.4 times 10 to the negative 5 molar, which is our hydroxide concentration, which is why we did the ICE table, because we need to know the hydroxide concentration. Once we get that, we can take the negative log of the hydroxide concentration. It'll give us a value, and we can subtract that from the pH, which is 14, and that will give us our pH. So remember, when you're dealing with bases, you're dealing with pOH. You're not dealing with pH. And that will give us the pH of 9.37. So again, when you're dealing with the base, you're getting the hydroxide concentration. So you need to, if you're using it this way with the hydroxide, then you need to remember that this is a pOH, and you subtract it from 14 and it'll give it the pH. Okay, so if the cation or anion in a salt is a weak base or weak acid, the salt will have acidic or basic properties. So it's the opposite of what you're dealing with. If you have a weak base, then the salt will be acidic. If you have a weak acid, then the salt would be basic. The anion of a monoprotic strong acids in group 1 and 2 cations have no acid-base properties, so they're neutral. They don't play a part. Some metal cations with high charge or small diameters can act as proton donors because they hydrolyze water. They become hydrated with water, which is just a fancy word for they're attaching waters to it, and then it gives the ability to donate one of the protons from that water. The Ka and Kb are related through Kw, which is nice because we've been using this over and over again. So even if we're doing different topics, we're still using the same calculations in the same way. The pH for a salt can be calculated in a manner that is similar to calculating the pH of a weak acid or weak base given its concentration and ionization constants.